The telemetry stopped changing while the mission was still flying toward Pluto. Inside the operations center at the Johns Hopkins Applied Physics Laboratory, the display froze. The clock did not. Every passing second carried an unsettling implication. The spacecraft was more than 4.5 light hours away. Whatever had happened out there had already happened hours earlier. Alice Bowman and her team were not watching a crisis unfold. They were discovering one that had already run its course. Before anyone on Earth could send a single command, the spacecraft had been left entirely on its own. The question was no longer whether engineers could save it. It was what the spacecraft had already done while no one was watching. For a little more than an hour, nothing came back. The radio signal vanished into silence. New Horizons had been expected to execute a carefully prepared sequence as it closed on Pluto. Instead, its primary flight computer became overwhelmed while handling simultaneous data compression and command sequencing. The processor locked in place. Communications stopped. At that distance, no emergency reset from Earth was physically possible. Even if Mission Control had recognized the failure the instant it occurred, every command would still spend more than 4 hours crossing the solar system. By then, Pluto would already be behind the spacecraft. The mission could have been over before anyone on Earth knew it had begun to fail. Deep inside the spacecraft, another clock was already counting. A watchdog timer kept checking whether the primary computer was still responding. Eventually, it concluded that something was wrong. Without waiting for permission, it shut down the failed system, started a completely independent backup computer, entered safe mode, stabilized the spacecraft's orientation, and preserved its ability to communicate with Earth. These were not creative decisions. They were deterministic fault protection rules written years before launch, each triggered only when specific conditions became true. When the first recovery signal finally reached Earth, engineers were receiving evidence of 2 moments at once: news of a failure that had happened hours earlier, and confirmation that the spacecraft had already survived it. That small safe mode indicator had become far more than an alarm. It showed that responsibility for survival had shifted away from Earth. The farther spacecraft travel, the less useful immediate human intervention becomes. Communication delays stretch from minutes to hours, and eventually to nearly an entire day. The speed of light never changes. Human reaction time cannot outrun it. With every additional mile, more responsibility passes to the spacecraft itself. Long before Voyager crossed into interstellar space, engineers at the Jet Propulsion Laboratory understood that limitation. They built the spacecraft around redundant computers, capable of isolating certain failures without waiting for instructions. Separate systems handled commands, scientific data, and spacecraft orientation. If one memory path became unusable, operations could be redirected through backup hardware already on board. The decision happened inside the spacecraft, not inside Mission Control. By the time telemetry reached Earth, the emergency response had often already finished. The engineering drawings look surprisingly simple. Electrical paths branch toward duplicate hardware. One route fails. Another immediately takes over. The elegance is almost deceptive. Voyager carries only about 69 kilobytes of memory, millions of times less than a modern smartphone. Yet within that tiny amount of code lives the logic responsible for preserving one of humanity's longest-running scientific missions. The software does not understand danger. It compares measurements against predetermined limits. If voltage falls too low, if orientation drifts beyond tolerance, or if expected responses never arrive, another sequence begins. Every rule exists because engineers imagined a disaster years before it happened. By the time Cassini reached Saturn, survival had become an engineering requirement rather than an added safeguard. During orbital insertion, Saturn itself blocked direct communication with Earth. The spacecraft disappeared behind the planet while performing one of the most dangerous maneuvers of the mission. Engineers could not guide it through the burn because they could not even hear it. Autonomous fault protection routines stood ready to switch to redundant thruster systems if critical valves failed during the maneuver. Cassini had to complete the operation alone. Only after it emerged from behind Saturn could Earth learn whether those decisions had been necessary, or whether the mission had survived at all. Elsewhere in the solar system, another spacecraft lives under a different kind of deadline. The James Webb Space Telescope must keep its enormous sun shield precisely between its mirrors and the sun. If that orientation is lost for too long, heat begins reaching instruments that operate only a few degrees above absolute zero. During a software anomaly affecting its attitude control system in December 2022, Webb entered safe mode automatically. Scientific observations stopped. The telescope shifted its attention to something more urgent, maintaining thermal stability. Only after its orientation had been secured could engineers investigate the fault. Safe mode was no longer preserving communications alone. It was protecting the observatory from irreversible physical damage. Back on Earth, the first visible clue often arrives as a faint radio carrier captured by one of 3 giant Deep Space Network antennas. A 70-meter dish slowly pivots beneath the night sky. Somewhere billions of kilometers away, a transmitter no stronger than a household light bulb sends back a carefully rationed stream of data. Packet by packet, status information fills the display. One familiar condition appears again. Safe mode active. To engineers, those words no longer describe failure alone. They mean the spacecraft is alive, electrically stable, pointing toward Earth, and waiting. Even so, autonomy has limits. Late in 2023, Voyager 1 began returning unreadable telemetry after a corrupted memory chip damaged part of its flight data subsystem. Safe mode and the spacecraft's fault protection routines could preserve the mission, but they could not repair failing hardware. Engineers spent months diagnosing the problem across a one-way communication delay that now exceeds 22 hours. Every test required nearly 2 days before its result could even be seen. The spacecraft kept itself alive. Restoring its capabilities still depended on people separated from it by billions of kilometers. The green safe mode indicator appears almost ordinary. At first it signaled that something had gone terribly wrong. Later, it became confirmation that the spacecraft had stabilized itself before anyone on Earth even knew an emergency had begun. Today, it still appears in telemetry, crossing the darkness between worlds, carried by radio waves that travel for hours before reaching a waiting antenna. Long before those signals arrive, the decision has already been made.